Now, so why do we even need QC then? So actually, in practical sense, why do we need QC is that when we have a reaction, if a reaction goes really slow, we don't really know if it has reached equilibrium or not. What can we do is we can actually measure the concentration of each component, products and reactants alike, and then calculate the QC of that reactants of that particular system. And then we compare that QC with the historical data given in terms of Kc for that reaction under that temperature. Then we will know if the reaction mixture has reached equilibrium or not. Okay? So if your QC is smaller than Kc, it means this reaction is going to go forward a little bit so as to produce more products. If your QC is larger than Kc, it means you actually have more products. The reaction is actually going backwards at that moment, and it will, once it reaches equilibrium, contain more reactants. Okay? So it's really in a practical sense, especially when a reaction is slow, we don't know if the reaction has finished yet, then we measure the concentration and calculate the QC and compare it to Kc. If QC equals to Kc, it means this reaction, reversible reaction, has finished. Okay. So another good thing about Kc is that by recording the Kc for a particular reaction at a given temperature, we're able to know if this equilibrium mixture is going to have a lot of products or a lot of reactants. Okay? That's very important for industrial production. So for example, we basically manually define when Kc for a given reaction at a given temperature is larger than 10 to the power 4, it means your equilibrium mixture is going to have a lot of products. So in terms of industrial production, if products is what's desired, then this reaction is worth going ahead. Okay? On the other hand, if your Kc is smaller than 10 to the power of -4, it means when the reaction reaches equilibrium, it will have a lot of reactants. So in terms of production, if I added a lot of reactants, but in the end, there's still a lot of reactants, it means this reaction is not suitable for industrial production of a particular product. Yeah? Okay. However, for anything between 10 to the power of -4 and 10 to the power of 4, we think that reaction is likely like a reversible reaction. So those kind of reactions are the real reversible reactions. It means that when the system has reached equilibrium, in the system, there will be significant proportion of products as well as significant proportion of reactants. Okay? So those kind of reactions are what we want to manipulate so as to obtain the desired products. We can manipulate through maybe, increasing the pressure, increasing the concentration of reactants, or removing products if the product is actually desired. Okay, so make sure that to make the reaction keeps going forward. So those are the reactions are real reversible reactions that we can manipulate. Okay, so Kc tells the proportion of products over reactants at equilibrium. Okay, it gives an indication of the extent of a reaction when it reaches equilibrium. Okay, so then let's compare extent and rate. We're going to use what we have learned in Unit 2 about strong acid and weak acid. So just to refresh your memory, an acid is strong when it ionizes completely if you put it into water. Okay, so almost 100% of reactants are turned into products. So that's a high conversion rate. That means the extent of the ionization of a strong acid is high. So those reactions will have a really high Kc value. Okay, so one of those example is hydrochloric acid. So if you put hydrogen chloride into water, and then it will ionize almost completely. And as a result, this reaction, this reversible reaction, has a high Kc value. On the other hand, if we look at ethanoic acid, that is vinegar, okay, it's a weak acid. So weak acid means when you put that into water, they do not ionize completely. In fact, actually 99% of the vinegar, the ethanoic acid molecule, does not participate in the reaction. That means this reversible reaction has a low Kc value. It's a low conversion rate. That means the extent of the forward reaction is low. Okay, so based on these two descriptions, can you tell me which reaction happens faster or which reaction happens slower? Would you know? You wouldn't. Okay, so the extent of a reaction gives no indication to the rate of reaction. So I have no idea which reaction will reach equilibrium faster and which one will reach equilibrium slower. Everything that I have described here, I'm describing the extent of the reaction rather than the rate of reaction. Okay, so even if the reaction goes really complete, there is no indication to the rate of a reaction. Okay? And also, a reaction can proceed really far to reach equilibrium. Yeah, it will have a high conversion rate, but it can also happen really, really slow. Okay. One more example is if you remember the decomposition of hydrogen peroxide. H2O2, yeah? We said without catalyst, that reaction would take forever to complete. But it will complete. After a year, your hydrogen peroxide will all turn into water. But it takes a whole year or two years to do that, okay? So that reaction can be complete. It will have a high Kc value, but it can happen really, really slowly if you don't put catalyst into it. All right?